Alright, hello everyone. This is gonna be the final review video. I'm gonna be doing the first final that's in the course website. I believe the 2021 version, if I remember correctly. Yeah, the 2021 version, 21 spring. Alright, let's just start. So, we start with some truth tables. It says P and Q or R with the biconditional with P and Q and R. So now we'll do Q or R. So this would be true. Remember, for the or, at least one of them has to be true. It's only false when both of them are false. Now P and Q or R. For and, both of them have to be true. Alright, so now we'll do the biconditional between these two. So I don't really have space, so I'm just gonna say it's basically the biconditional between these two guys. So I'm just gonna make a new one down here. And biconditional is true when they both have the same truth value. Yeah, so if it's false, false, or true, true, that results in a truth value for the biconditional. So that's that for that question. Next question is another truth table. So P arrow Q. Remember, this is only false if it's P is true and Q is false. Exclusive or, remember, this means that only one of them can be true. If both of them are true, then it's false. Alright, so this is the final one. I just put some dots here because I didn't want to write it out, but that's this basically. Alright. Let me just double check that. I think I might have done something. Let me just double check this. T T T T F. P R Q. Nope, this should be true. Actually, wait, no, this should be false. False, true, true, false. Okay, I think this should be right. I tend to make some mistakes on truth table sometimes. There's a lot of stuff to look at, but I think that's right. Alright, moving on. Oh shoot, I duplicated this one, so I think. So let me just bring this up here. Alright, so number 3. Mention whether the following statements are true or false, and you don't need to give a reason. Alright, so let's do this one by one. So A, and this is a table I'm using from the lecture slides. They basically give the answers to all of these questions, like all of these ones are within this. So this would be good to memorize. Alright, so A, P or not P is a contradiction. So let's try and find that in the truth table. And we found it right here. It is indeed a tautology, so it's actually a tautology, so this is false. B, P or P and Q equals P and P or Q. Let's try to find this one. So we see here that this is basically P And this is also P, so this is true. That's right, because they're both P. They both come out to P. Alright, part C. A contradiction is equal to P or a tautology. You can see right here though, P or a tautology is a tautology. So this is false. D. P and P is equal to P or P. And we see right here that that is indeed the case. P and P is equal to P, and P or P is equal to P as well. P and a contradiction is equal to the negation of a tautology. So we can see that P and a contradiction is equal to a contradiction, which is, a contradiction is the same as the negation of a tautology, because a tautology is everything is true, a contradiction is everything is false, therefore a contradiction is the negation of a tautology, so this is also true. Alright, moving on. Next question is that prove that the sum of the squares of any two consecutive integers is even. Odd integers, right? Yeah, odd integers. Any two consecutive odd integers is even. Prove that the sum of the squares of any two consecutive odd integers is even. Right, so what do you remember about odd integers? Odd integers can be represented as 2k plus 1, or 2k plus 3 and so on, right? So we could say that the sum of the squares of two consecutive odd integers would basically be like this. These are two odd integers that come right after another, and we're squaring them, right? So this comes out to 4k squared plus 4k plus 1 plus 4k squared plus 12k plus 9. This comes out to 8k squared plus 16k plus 10. You could take out 2 from this to make k squared, 4k squared plus 8k plus 5. And then this is just, since addition and multiplication is closed on integers, this is just some other integer y. So this will come out to 2y, which is the definition of even, right? So that's that for that question. Moving on. Suppose x and y are real numbers. Prove that x equals y if and only if y is equal to x plus y squared divided by 4. So, in order to prove something like this, you first need to prove that the left-hand side equals right-hand side, then right-hand side, left hand side equals the left hand side. So we'll do the first step first. If x equals y, if x is equal to y, then x times y would basically be y times y. This would be y squared basically just be y squared, right? And then that's how it is here. And now if we do x plus y squared, sorry, let me put this down. X plus y squared divided by 4, where x is equal to y, so this would be 2y, y plus y squared over 4 turns to 2y squared over 4 equals 4y squared over 4. These cancel, so y squared equals y squared. You see, I just said, okay, x equals y, so we do xy, the left hand, this side of this equation, that comes up to y squared, and then plug in those same values on this side of that equation, and then you get y squared as well. So this proves it from the left hand direction, the left direction to the right direction. So now we'll prove it going the opposite way. Alright, so x, y equals x plus y squared over 4. 4xy equals x plus y squared. You square x plus y, you would get right, that's what you get on that side. Then subtract this out. And then this is the same as x minus y squared. And if you factor this, you get x minus y, and the roots of this is just, and if you solve for the roots of this, x equals y, right? So we proved both sides of this equation, right? That if you have the left hand side, if you have left hand side, it goes to the right hand side, and then this is right hand side to left hand side. So since you proved that, both left hand side to right hand side, that basically proves, that's enough to prove for the proof of this question. Yeah, that's good for the proof of this question. Alright, next question. This is like an algebra type question. So it says, use algebra to prove that 0.318, 1818, and 18 keeps repeating, times 0.888, and that keeps repeating, is equal to 28 over 99. Alright, so let's do this. Alright, 0.318, 18 times minus 0.888 equals 28 over 29. Let's call these things x and y. So 100x, so we basically want to do some stuff to like get rid of these infinite numbers, right? So 100x would be 31.818. That keeps repeating. 10y would be 8.8888. 99x, so that would be essentially 31.818 minus 318. This is equal to 31.5. We got rid of there's no more infinite repetition now. It's just a normal decimal like this, so that's good. And now 9y will basically be 8.888 minus 0.888, and that's just 8. Alright, so we just got rid of the repetition. So 99x is 31.5 and 9y is 8. So what does that mean y is? Y is equal to 8 over 9, right? And x is equal to 31.5 divided by 99. Simplify that comes out to 7 divided by 22. Right? So if we now take this 7 over 22 times 8 over 9, we get 56 over 198, which simplifies down to 28 over 99. Alright. So let me just double check something real quick. Yeah. So what we did here is basically just find a way to represent those infinite repeating numbers in fractional form. And then from there, some simple multiplication with fractions, and we come to the answer. Alright, next question. Now we're on to mathematical induction. Alright, so we have to prove that the summation of the sequence is equal to this. Alright, so first we'll start with the base case. Which would be, since it says n is greater than or equal to 1, the base case would include it would include 1, so it would be, you basically want to, okay, what's going on? One sec. Alright, so base case, we would basically want to prove that the left-hand side is equal to the right-hand side using the smallest number. So it would be, this comes out to 1, and this comes out to 2 minus 1, and 1 equals 1, so base case is true. Alright, so now we're on to the induction step. Where we assume PK is true for prove that pk plus 1 so now we'll begin to prove pk plus 1. Alright, so if you look at this summation, right, what's it doing? It's basically going from adding 1 times 1 factorial, 2 times 2 factorial, all the way up until k plus 1, right? So if we're going all the way up until k plus 1, that means at some point we have to cross k times k factorial, right? Because k is 1 less than k plus 1. Right? And what is this? This is essentially pk. This is what pk is doing, right? That's essentially what pk is doing. It's doing a summation up from 1 to k, right? So we can turn our pk plus 1 into pk plus k plus 1 times k plus 1 factorial. And we know that pk is, from our inductive hypothesis, pk is k plus 1 factorial minus 1. This turns to k plus 1 factorial minus 1 plus k plus 1 factorial. So let me just do some rearranging. I'll put this, the left-hand side on, the right-hand side on the left-hand side. Just some rearranging. Okay, so from here, we're going to have to factor out k plus 1 factorial. K plus 1 factorial times k plus 1 plus 1. Factor that out from there, right? And then if we do that, we'll get k plus 1 factorial times k plus 2 minus 1. Right? And what's this? This is essentially k plus 2 factorial, right? Because k plus 2 factorial is k plus 2, k plus 1, and so on, right? And then this k plus 1 factorial already has all that. So k plus 2 times k plus 1 factorial becomes k plus 2 factorial. And this is what we wanted to prove in our inductive hypothesis. So that proves that pk plus 1 is true. Yeah. Alright, so for this question, we have to find the induction. We have to do we have to do mathematical induction on Fibonacci sequence, where f of 0 is 0, f of 1 is 1, fn is fn minus 1 plus fn minus 2 for all n is greater than or equal to 2. First thing we do is find the base case. And we'll do this for n is equal to 2, so this would be f of 4, since it says f of n plus 2, that's 1 plus. So this is summation from 0 to 2. We know that f of 0 is 0, f of 1 is 1, and we don't know f of 2, so we'll find f of 2 right now. f of 2 is f of 1 plus f of 0, so that is 1. That's here, that's 1. This comes out to 1 plus 2, which is equal to 3. Right, so now we'll double check that. Now we'll double check that with the actual formula, where f of 4 is equal to f of 3 plus f of 2. We don't know f of 3 yet, so f of 3 is equal to f of 2 plus f of 1, which is equal to 2. So that means f of 4 equal to 2 plus 1, which is 3. And these both match. So that's good. Next, on to our induction step. So instead of n, we'll just say k here. This is 1 plus the summation from I equals 0 to k of f of I. And we need to prove that pk plus 1 equals Alright, so that's what we want to prove for pk plus 1. So pk plus 1 is basically fk plus 3, right? fk plus 3. And we need to prove this. We need to prove this using our original equation, the given equation, which says that f of k plus 3 is equal to f of k plus 2 plus f of k plus 1. And since we did in our induction step, in our inductive hypothesis, we said that assume this is true for some k is greater than or equal to 2. So f of k plus 2 fits within our inductive step, and everything less than this is also within our inductive step. So we said f of k, p of k is in our inductive step. That means everything less than k is also within it. So that means k minus 1 and so on, right? And p of k minus 1 is just f of k plus 1. This is f of k plus 2. So both of these guys are within our inductive step. So, right, so this is just p of k and this is just p of k minus 1. Right, so now we can transform these. Where p of k plus 1 is equal to one plus summation from k I equals 0 of f of I plus summation k minus 1 I equals 0 f of I. Or rather, we could just say, we just keep this as f of k plus 1. f of k plus 1. If we just keep this at f of k plus 1, it actually becomes a lot simpler to see. So this is the summation from all things f of 0, f of 1, all the way up to f of k, right? And then now we're doing an plus f of k plus 1. So what does that look like? That looks like the summation. That looks like the summation from I equals 0 to k plus 1 of f of I, right? So this can turn into basically right? So if I lost anybody, what I basically did was I said, what is that? What is the summation of f of I to k? So that's f of 0 plus f of 1 all the way up to f of k, right? That's the summation. Now we're adding it with f of k plus 1. So now I'm saying, okay, what does that look like? What is that? That's the summation from I equals 0 to k plus 1, isn't it? Right? And so that's what I did. And that is what we wanted to prove. So that is our answer for that question. Our next question. Write the pseudocodes for the recursive algorithms for solving the Towers of Hanoi problem and computing the greatest common divisor for two integers. So this is straight from the lecture slides. Like even it's not even like I keep this in the back of my mind either. Just if you want, you could just remember it from the lecture slides, and the definition I'm gonna say right now is straight from the lecture slides as well. Like, you don't really need to give much thought to this. You just gotta remember it, I guess. So for the greatest common divisor, it's GCD AB into a function where yeah, this is straight from the lecture slides. I'm just put this definition here if anybody wants to see it. I don't know if this could be on the test, but yeah, it wouldn't hurt to know this. It wouldn't hurt to memorize this. It's not too much. And then for the Towers of Hanoi, it's like for k is greater than or equal to 2, something like transition the top thing. Oh, what? Transition the top. Alright, 1 second. Let me just look this up again. Right, so move the top k minus 1 disks from A to B, and then the second one is move the bottom disk from A to C, and then it says to transfer the top k minus 1 from B to C. Like, you don't really gotta know what that means. I just remember it. Yeah, even me, like, I straight pulled this from the lecture slides. Like, I don't know this myself. But yeah. next question. Next question is question 9. Alright, so here we just see if they're one-to-one or onto for each of these functions. So let's say a is 3x z to z. Is this one-to-one? First is this one-to-one. So basically we'll do something like this. We'll do something like this, and then to show this one-to-one, cross those out. X1 equals x2, so yeah, it's one-to-one. This is one-to-one, but this is not onto. This is not onto because every member of the output set cannot be mapped. Right? Meaning, like, for this function, we can never get 1. 1 will never be mapped. The number 1 will never be mapped by this function because it goes from integers to integers. So if it's a one-to-one and an onto function, each integer would have should have a corresponding input, but the number 1 cannot ever be mapped within the set of integers. So this is not one-to-one. Sorry, this is not onto. Alright, so next part. 3x r to r. So we already showed that before it is one-to-one. We showed that before, and now, since it's in the set of real numbers, we can use decimals. It is also onto. Alright, so because now the number 1 can be mapped because we can use 1/3 in place of x, right? We can now use decimals, so every number will end up getting mapped. Alright, so you don't really, this one says you don't need to give an explanation. Alright, so you just gotta like say it. Alright, so this is 3x squared. 3x squared instead of integers to integers. So if we do something like this to show that it's one-to-one. So once you come up with something like this is obviously not the case. X1 squared is equal to x. Actually, no. When we do square root, x1 equals x2. This is not always the case, right? Because -1 squared is equal to 1 squared. So and -1 is not equal to 1. So this is not 1 to 1. And onto, let's see. And this is not onto either because let's say you can't, like, once again, you can't map the number 1 or even -1 as well. So this is not onto and not one-to-one. Alright, next is that same function, the set of real numbers to real numbers. So we already know it's not one-to-one. So changing the domain of a function will not like change whether it's one-to-one, but it could change if it's onto, basically. Oh, let's not say. Yeah, so right, so this is not onto either. The set of real numbers to real numbers, this includes negatives, right? And 3x squared, that'll never give you a negative number. So -1 cannot be mapped. So this is also not onto. Right? Yeah, that's also not one-to-one or onto. Alright, next, and not final, almost final. Alright, so this says consider the function which goes from r star to r star. It's a set of all non-negative real numbers such that f is a mapping from pounds to kilograms. A kilogram of mass in the international blah 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 is 2.204 pounds. So 1 kg is equal to 2.204 pounds. Is f a one-to-one correspondence? So all this function is doing is taking some number of pounds and multiplying it by 2.204. Right, so that'd be 2.2. This would be 4.4 and then 6.6 or whatever, right? This is just 2.2. This function is just 2.2x, right? So, and this is obviously one-to-one correspondence. In this set of real numbers. So this proves that it's one-to-one. Now to prove it that it's onto, we'll do something like y equals 2.2x. So x equals y over 2.2. F of y over 2.2 equals 2.2 times y over 2.2. These cross out. F of y over 2.2 equals y. So that proves that it's onto as well. Right. I just use the normal methods of proving something is one-to-one and onto. But yeah, that function is literally 2.2x maps pounds, mapping pounds to kilograms. Right. So yeah, that's that. Next question. The set of all people, let A be the set of all people and R be the relation defined on A as follows. For all persons P and Q and A, we have that PRQ, where P has the same birthday as Q. Is R an equivalence? Is R a equivalence relation? And if it is, what are the distinctive equivalence classes? So recall what a equivalence relation is. Equivalence relation means transitive, symmetric, and reflexive. So this means that if we have PRQ and QRR, let me put this down, then symmetric means PRQ, QRP. And reflexive means this is true always. Alright, so let's prove these. Let's see if this thing is a equivalence relation or not. So transitive, this relation is obviously transitive. If a person P has the same birthday as person Q, and Q has the same birthday as person R, then P, of course, has the same birthday as person R as well, right? If I have the same person as another guy, that other guy has the same birthday as somebody else, I have the same birthday as the other person as well. Birthdays, like, no matter what, it's gonna be the same. So symmetric, if P or R, then it follows that R or P. So let me just use Q instead. So if I have the same birthday as my best friend, and then my best friend then that obviously means that my best friend got the same birthday as me, right? So that is symmetric. Reflexive. P or P is always true, right? So I'm always gonna have the same birthday as myself, so that is reflexive. Right, so we know that now it is a equivalence relation. We know that this relation, so the distinct equivalence classes of this would be each day, basically, right? So this is the set of birthdays. Like, the relation is a person having the same birthday as another person. So each class would be each day containing the set of people whose birthdays are on that day, right? So each equivalence class for such a function like this, where we're talking about birthdays, each distinct equivalence class would be each day, and that would contain the set of all people whose birthdays are on that day. And that is the answer for that fun. That is the answer for that question. And that's it for that. That's it for that test. Alright, so this one wasn't too bad. Similarity-wise to your real final, I have no idea. But this is good practice. And yeah, good luck. Good luck to everybody on that test tomorrow.